Okay, today we have the first seminar, so we are happy to have the Dr. Apicharttrisorn here. So he's from the Nokia Bell Labs in New Jersey, and his research is in the mixed reality and the low latency control and also network system. So please join me to welcome Dr. Apicharttrisorn to give us a talk.
No. Okay. All right. Thank you. So thank you so much for having me here. This is my first time in Delaware, except when I was driving past to the Washington D.C. This is my real first time, and first time in University of Delaware, and a nice campus. Thank you so much. So a little bit of my background. I am a network researcher at Nokia Bell Labs. I previously was a postdoc researcher at Carnegie Mellon. I got PhD in computer science from University of California, Riverside, and I'm working on a network system in general and also mixed and extended reality. So this year, this is the first seminar for you, right? Very good timing for this year because we are celebrating 100 years of Bell. Imagine 100 years, what happened, right?
We're setting the stage for the next century of limitless imagining. For 100 years.
Why Snoop?
100 years, Bell Labs has been a pioneer of progress. We've harnessed our extraordinary imagination to fuel visionary breakthroughs and shape the future of technology, solving humanity's most pressing challenges. We created the first transistors and lasers, connected the world through the Telstar satellite, built the foundation for today's digital age with information theory, and developed artificial neural networks for machine learning. Our work has fundamentally changed how we live, work, and communicate. Today, as Nokia's Global Industrial Research Lab, we're setting the stage for the next century of limitless imagination, disruptive innovation, and real-world impact. We're unlocking the potential of responsible AI to transform networks and industries, solving the unsolvable problems with quantum technologies, advancing a 6G future to connect a hyper-digital world, giving us a sixth sense, and establishing the first cellular network on the moon to pave the way for a sustainable human presence in space. Nokia Bell Labs has made great change happen, and we're inventing the technologies that will define tomorrow.
Yep, and we just celebrate.
For 100 years, Bell Labs has been a...
Okay. We celebrate this 100 years of Bell Lab in Murray Hill, New Jersey, our Bell Lab headquarters. And in that celebration, we invited a lot of distinguished guests. We have Nobel laureates. We have the distinguished engineer professor who received National Medal Award, whatever you name it. Right? So I get a chance to meet some of them, 6 of them here. This is me right next to the gentleman number 1, right? And despite their achievement, I'm impressed that they pay attention to our low latency demo, right? Okay, right. They pay attention, ask good questions, try out our demo. It's very inspiring that you never stop learning, right? With even their age or whatever you can see, right? So this is actually one lifetime experience I have with this 100-year celebration. Otherwise, this professor wouldn't come to New Jersey, right? So, and looking, yeah, I actually have yeah. The gentleman number 1 is Daniel Fisher. He was a AT&T Bell Lab member of technical staff. He's a professor. He was a professor at Stanford University. Number 2 is Tom Maceta. He's a Bell Lab until 2018. is a distinguished professor at NYU. He originator of the Massive MIMO, if you know the antenna wireless thing, like Massive MIMO, and he's a member of National Academy of Engineering. Okay. Number 3 is Robert Wilson, discovered cosmic background radiation and proved the Big Bang theory of the universe. He was awarded the 1978 Nobel Prize in Physics. Number 4 is Horst Stromer, is the physicist, Nobel laureate and emeritus professor at Columbia University. Number 5, Dave Bishop, ex-Bell Lab. He's now a professor at Boston University. He's a member of National Academy of Engineering and National Academy of Inventors. 6, Stephen Chu is an American physicist, former government official. I think he was a Department Secretary of Department of Energy, I think. He's a Nobel laureate and 12th Secretary of Energy, right? So yeah, it's all been very, very nice, very curious about whatever we have at Bell Labs at the celebration. Because we have like different demo, but this is the demo that my department is responsible for. Okay. And looking forward, right, we are moving to a new office next to Rutgers University in New Jersey. We're moving in like 3-4 years, and we aim to be in innovator hub in New Jersey. We have like a Bell Lab office. We have some research lab from Rutgers move in. We have some company, doing collaboration with Bell Lab, supported by state of New Jersey. And next to our new building is the Rutgers Health. They're doing like medical research. And for you guys, we have multiple internships every year, right? So look, you know how to look for internship, right? And consider, this is just example from my team, right? Previously, you have the adaptive pipeline coding and streaming, and student already published, right? And this is the recent project we have with our intern to the driving over for network condition. If we have some time, I'm gonna talk about that a little bit. And coming back to Bell Labs, right? 100 years of innovation, and like just this phone, right? So many of the inventors is inside your phone, right? Everyone has it, right? The transistor information theory, the communication, we wouldn't have this like 5G or like high-speed communication without this information theory, right? And satellite, who knows what charge coupled devices are? What is that? What are you using? I think you use it every day, right? No? No one knows charge coupled devices? It's a camera, right? CCD is the sensor of a camera. And
people know CCD, but we don't know CCD.
Right, yeah.
You CCD camera.
Yeah, in the camera, right? And the UNEXT, right? The operating system, your Android or your iPhone built on top of this UNEXT, right? And a lot of driver, a lot of applications with C++, right? Invented in Bell Labs. And also neural network, right? When Jan LeCun of Meta was at Bell Lab, he invented this neural network. So a lot of invention happened in our lab, and let's look at this Dennis Ritchie and Ken Thompson, who invented Unix and the programming language. And I had a chance to fit in the room where they work on Unix and C++. I work in the same building. It was like outside this room is a large room where they have houses. I think they use this area to discuss ideas, hang out, have coffee, talk, and when they're working, they go inside the rooms, smaller rooms, work on this thing. So it's a foundation of operating system, right? That control or harmonize multiple components in your single machine, right? But how about like the application today where you have more type of sensor actuator in the industry, you have also advanced sensor in your immersive application, you have more better radio, you have a new transport network. You need a newer idea, from UNEXT that you need this thing to work together, right? Like unified system that is simple, secure, scalable, and sustainable. So from the limited knowledge sharing, you want to have more knowledge and data services from the application that is written by a single stakeholder. Right now we have like more decentralized environment, right? For example, when you pay something online, a lot of things happening behind the scene, right? Like with multiple stakeholders in just one service. And you have more alternative service, instead of exactly how to use, but you can express it as your intent, right? And then use whatever discovery service for your application. We need to have some extended compute services where the compute network work closely together. And the network and application has to be aware of each other so that the performance can be optimized and the product experience can be guaranteed, right? We call it UNEXT, right? Unified Network Experience, which we want to extend the idea from UNEXT, right, to have the more scalable vision for the network application. And you can find out more about the UNEXT on this website. So this project that I'm talking about is part of the UNEXT project. It's called PointPresence online habitat for multi-user mixed reality telepresence. Application compute network symbiosis, right? So when you look at like mixed reality application, right, you can think about like maybe some industrial application or some teledriving application or some medical application, right? That the user can see some 3D content in real time and interact with that virtual environment, right? And that usually you have a user, you have to connect this user over the internet, and a lot of network requirements to support that application, right? Some work already look into how you can reduce the network requirements, right, by using some segmentation and compression and stream the data over the internet, over the network. And some work only look at compute, right? If you look at these communities, right, that can scale the compute up and down for you, right, without knowing anything about application. We have this new component called camera selection, right, that look to reduce both the compute and network workload for the MR application. We have the reactive opportunities that look into the compute runtime of the CPU and GPU tasks and be able to adapt the workload for those tasks in runtime. And finally, reduce the network workload as well, right? So we combine all this together and we call it PointPresence, our framework for multi-user telepresence. Okay, let's come back to the use case, right? You have the 3D physical environment, right? You have your office, your home, or even this auditorium, and you want to use the MR or immersive application. You need to install the multiple 3D cameras, right, around the environment that you want to use. And we're not considering like 3D avatar or the head model, right? We're streaming the physical object in the physical world, right? So that those user can move freely in the space and, can interact with any user at any time. Okay. And a common configuration could be, you have like a 360 capture and you deploy 8 cameras. Right? Like in this, you have 2 users, right? And you deploy 8 cameras to do 360-degree capture. For example, you can have the set camera or RGB cameras, and the blue triangle represent the field view of each camera, right? In order to have 360 capture, you have to have 8 cameras. And this 8 camera stream sent to MRH, right? H means the small compute unit that you have close to you, right? Because when you send wireless Wi-Fi or 5G, you need to have MRH compute nearby, right? So that you can reduce the latency perceived by the application. You stream this 8 camera stream to this MRH, and the MRH process them, merge them into a 3D model, as for example, point cloud, and send to the rendering device. For example, HoloLens, right? And the second user is doing the same thing, right? Uses 8 camera, right? And then stream to another MRH and send the 3D model back to the first user rendering device. Okay. And what's the problem? So the problem doing this type of MR person is the following. The first, we have a high compute demand, right, for concurrent multiple cameras. So because this MRH has to process multiple camera at the same time, it increased the CPU and GPU usage at the MRH, right, and can lead to long latency perceived by the other user. It has to process camera concurrently, and all the camera stream should have similar latency, right? Otherwise, you're going to have distortion. Some cameras send out later, it cannot be merged, or if it merged with other camera, then the 3D model will be started because the object that you're looking at is moving, right? It's dynamic. So MRH has to support multiple scenes, right? I'm talking about like 8 camera per scene. Then if you have 3 scenes on this camera, for example, right? MRH has to process 24 cameras, or you have more than that. It's gonna increase the workload of this MRH significantly. Okay, our preliminary measurements show that in order to keep 30 frames per second, right? The number of camera can be only 5 to 6 cameras, right? For the frame latency to be, at around 33 milliseconds. Okay, and this is on, like a high grade server, right? Edge server, like has A100 GPU and has high grade, high tier CPU as well. The second problem is the unpredictable compute demand, right? Because your compute demand depends on the user context, right? Remember the MR user, right? That looking at your 2D model, that user can move the field view, right? Can look around, and that field view will give the context of the user, right? And that can change at any time, and it's unpredictable. Because it related, because the subset of camera that capture that 3D model, if it's similar to the field view of the remote user, that should have highest priority or highest resolution, so that the user can see the 3D model with high visual quality. Okay, and also the point resolution change with the object distance from the camera as well, right? So when the camera has the different resolution and the object move closer or further away from the camera, it's gonna have a different number of points that represent that object. Okay, we need like a highly flexible pipeline, right, to this that react to CPU, GPU compute demands in a millisecond time scale, right? If you look at those cost scaling approach like Kubernetes, it could take up to a second to adapt, right? Which is not good enough for this MR application. And the last problem is the high GPU contention. So if you have the camera and capture the scene, right? If you're not doing segmentation, meaning that we stream all of the data through the internet, you're going to need around 3 to 5 gigabit per second of network, right, to support that stream, which is, this is very hard, right? Very challenging, even with the latest Wi-Fi technology, right? This is the impossible throughput for the network to support it. Then you need to, segment the scene, right, so that you stream only the object that you care about, right? For example, if I'm, doing telepresence, maybe the person in the scene is the most important object, right? So if you want to do segmentation, means you require a ML model, right? You need some form of ML model that running on the MR edge. And if you have multiple camera, then you have to process those 30 frames per second stream, right? And you have to run this machine learning on every frame. Then the latency incurred by this GPU contention is going up from 40% if you're processing 3 camera, right, to 65% if the MR is processing 16 camera. So the GPU contention is a big issue for MRH. So our system, our framework design principle is the simplicity and efficiency, right? It has to be simple enough because this decision you have around like 33 milliseconds, right, to process and make any decision you have, right? We cannot afford to deploy some complicated algorithms for this MRH. And efficiency means that every decision we make, it needs to have like immediate and multiple impact to the system. And our framework is deploy at MRH like ORAN rig, like a RAN intelligent controller that like 5G base station, right, or some enterprise server to support multiple 3D cameras, multiple scenes. And our work has these 2 key features: intelligent camera selection and reactive pipeline design. At a high level, right? At a high level, this PointPresence framework reduce bandwidth and compute requirements for MR, right? We have this module called camera selection, right? That select the camera that's most relevant to the user field view or the user context. And the outcome of this module is that we can reduce both the network bandwidth and compute workload, right? Because now we don't have to stream all the cameras, we don't have to process all the camera streams. Because we only process a subset of the camera. The second module is the scene segmentation. Right? The purpose is to segment the entire scene into objects and only stream the object that we are interested in. The outcome is that we can reduce the network bandwidth because now we are not streaming everything, right? Using this scene segmentation. The last one is the point cloud compression, right? That is like, okay, take the raw point cloud. Point cloud is like a 3D, like similar to the 2D pixel in your like YouTube or Netflix video, right? But each unit is a point in 3D. That is a point cloud, and usually it takes a lot of data size for each object, and using the compression technique like KD3 or OC3, right? We can reduce the data size of the point cloud significantly, and then we can stream over the network, right? So that is the the outcome of this point cloud compression is to reduce network bandwidth about 10 to 20 times. All right, so for the intelligent camera selection, right, let's go a little bit deeper. We have this user B, right, that look to the right-hand side of user A. Then the right-hand cameras of the user A are activated, and the user A do the same thing, like look to the left side of the user B, right? Then the left side cameras are activated, and the rest of them can be deactivated, right? That is the idea of the camera selection, and it has to be quick enough when the user change field view. It has to adapt to that changing context. All right. The key idea is to select the camera that's most relevant to the user field view, right? And streaming three cameras instead of 8. And our reactive pipeline design, let's look at the pipeline first, right? What is the pipeline for this MR Telepresence? We have the 3D world, right? We have the camera, multiple camera that capture this world, and we have to segment this scene into objects. And for each object, we have to compress the point cloud to reduce the network bandwidth requirement. And then, that is the task for encoder or the sender MR edge, right? That's sent to another edge called decoder or the receiver side MR edge. That do the decompression, do the point cloud merging, from multiple camera and render to the rendering device. If we can have the the most heavyweight task in this pipeline is the scene segmentation and point cloud compression. We discovered that the scene segmentation is GPU heavy. It's used a lot of GPU. That is expected because we are running ML model, right? It usually run more efficiently over GPU. Then the GPU task is mostly the scene segmentation. And point cloud compression is mostly happening on the CPU. So if we can kind of monitor the latency of these two tasks, right? First, we monitor processing latency of this scene segmentation, right? How long it takes to finish processing this scene segmentation per frame. Then if it's longer than our boundary or our expected latency, then we can adjust the ML frequency or the ML workload, right? Remember that usually for the 30 frame per second camera, you use the GPU to process all the frames, right? But if the GPU is congested, then we can reduce. Okay, maybe we process every 10 frame, right? We run this scene segmentation every 10 frame or every 5 frame, etc., right? To adjust the workload of this scene segmentation, under assumption that the object is not moving quickly between this frame, right? Between these 33 milliseconds. If also we can monitor the processing latency of this point cloud compression, right? How long does it take? This is not like modeling or anything, right? It's just at runtime. Then the streaming is doing this processing. We can monitor that how long it takes to compress point cloud, right? And we can adjust the resolution, right? If it's taking too long, then we reduce the number of points from, for example, 1000K to 50K, right? So that the point cloud compression latency is kept within the bound.
So this is under the context of two-person peer-to-peer. But if you have a group, if you're interacting with multiple people, and each one will be feeding into your MRS.
Yeah.
Would that be contention? 1 per hour, if they're all changing at the same time.
Yeah, in that, yeah, this is like a kind of multi-peer, but if in the kind of multi-task scenario, right? When you have one user like then into multiple users, then you can combine one way to like estimate the overlap field views for all of them, like union of them, right? And then choose the camera and compress them at one frame to all of them. maybe use some multicast communication technique, right? That you can send stream and then you get multicast over the network, and all the user will see the stream and look. They're gonna look at a little bit different, right? Than the other with this point. Then if you do that, there's no not much contention, right? But if you do like a user and you process one at a time, then it can be a little bit problem. And we have the end-to-end architecture and implementation, right? We have this encoder, right? That we have the parameter that we adjust is the GPU or FPS or ML frequency, and the point cloud resolution or point cloud size that we, this the knob that the control plane can control. And we have the control plane with the scene manager, right? Which kind of like take care of all the camera in the scene. For example, all the 8 cameras, and look at this the latency of the key module that I just described, right? And update the point cloud resolution, update the ML frequency or GPU FPS, and then send to the decoder. The decoder has to do some like temporal alignment to make sure that the object is sent to this decoder is from the same time, right, at the source, so that when it combined, it merged this multiple camera together, it has a very good 3D model sent to the renderer, to the user in a virtual space. Okay. We do experiment on like I told you is MRH with 4 A100 GPU and AMD CPU core and half the terabyte of memory. We compare baseline and PointPresence, right? PointPresence, we have everything, right? Camera selection, reactive pipeline, scene segmentation, and point cloud compression. For baseline, we don't enable camera selection and reactive pipeline, right? We process all the camera. We don't adapt to the workload or the latency of those heavy compute tasks. And what the data set that we use is we use a 3D person in 3D room data set, right? We merge this. We place the 3D person in a 3D room data set and place a virtual camera around that person, right? And the user field view that we simulate is, continuously move around that person, right? This is kind of like a more challenging case for our system because the set of camera is kind of like continuously change, right? It's not like kind of static user. That is more easy for us. And then the metric that we interested in is the end-to-end latency, right? The latency from the time that the camera frame arrives at the MRH until that merged 3D model is ready to be sent to the renderer, right? That is end-to-end latency. And another metric is SSAM. SSAM is kind of like well-known metric for visual quality, right? You have the ground truth image, and you have the processed image, right? Compared and the higher SSAM, the better visual quality. In 3D, you have to render that 3D model to the user field of view, right, into 2D, and you compare the ground truth model versus the model that gets streamed through this PointPresence pipeline. And SSAM highest is 1, right? The lowest is 0. So the higher, the better. And we run experiment and collect more than 750,000 data points with different scenarios. We change the network bandwidth, we change network delay, we change the compute instance size, small, medium, large, and we have the object that move inside the scene, right? Because this is kind of like a simulated or a virtual environment that we can control this person, right? And we also change the camera resolution between, I think, 2 720 and full HD, which is 1080p. We find that our PointPresence reduce end-to-end latency, by 3.5 times, and a significant reduction in the end-to-end latency. And for 80% of the time, PointPresence stream 47% less number of points because of the camera selection. Right? And it achieved similar SSAM, so it shows that our system correctly and efficiently choose the camera to stream to the user, right? And when we measure the resource utilization on MRH, right? In this experiment, we run 2 scenes concurrently. So the MRH is pricing 16 cameras, right? We measure the CPU power consumption and CPU power consumption, and we can see that we can save a significant power by using our pipeline, right? Because we are not process everything every time. Especially the GPU, you can see, right, that it reduced like 4 times, something like that, right? And last, we want to show the robustness of our PointPresence. So we have this data set that we put 3 persons in the 3D scene, and the gray arrow line is the movement of the virtual user, right? Like the remote user that first is look at the object number 0, right? Which is still view number 0. Then you move from start to end, then you jump immediately back to start and change the view to 1, right? And come back again to view 2, right? We keep doing this to show that when there's abrupt change in the user code, right, or the virtual user view, our system can support very well. So you can see that this significant code change events are in the red line, right? Red lines. You can see that even with this abrupt code changes, we maintain a good visual quality and good frame per second for the end user. Okay. All right. This is this is the first project that I want to talk about. So we still have some time, right? So okay, that is the MRH that supporting the pricing of the camera, right? Sorry. Let me go back to this right. That we have this MRH that is closer to the source or the physical world that want to stream over this MR session. And we have another work that that we call a packet lake. And this is a network primitive for low-latency magnetic streaming, right? So even with the edge MRH that process the camera stream from the physical space, right? It gets streamed to the end user, and this end user may when it's getting the point cloud and then see it in the rendering device, when it changes the field of view, right? It may have to come back to the source server to get the 3D point cloud, right? And that can take a long latency and disrupt the user experience. So okay, let's like set that the context, right? That latency, even with this compute optimization that we have in the first project, right? We still have the challenge in the network, right? Because you can see that if you look at the core network, right, today internet, yeah, you have high bandwidth, this is good, but you can have high latency, right? Because it can span across East Coast to West Coast, or go to Europe, or to Asia. And you have the edge network, which is the last hop network that you have from your base station, right, to your mobile device. It has a low bandwidth, but low latency, right? If you have some kind of like edge switch, right, some network device that sits between this border, right, between a core and edge network, and we can manage this data stream of the 3D camera, and schedule what is the packet that is matched with the user context and sent to the user at the right time. Then the user can change the context, and this network switch can support that in real time, because now instead of user going through edge and core back to the source, right? Now interacting with this edge switch, right? Which is which gonna reduce the latency for the interaction significantly. Okay, and 2D video and XR or 3D video is different, right? In 2D video, you only have the temporal progression of your frame, right? You see Netflix, you see it continuously, and you only go back in time, right? You don't have the way to change the perspective, right? Or the spatial progression of a frame, right? As you have in this XR video, where you can go back in time, and you also can change the perspective of that 3D video, right? So this is so we need a new data structure and new network primitive to support this kind of video. And the target that we have is this 20 millisecond like motion to photon delay, because this rendering device nowadays can support like 60 frames per second, right? So the 20 millisecond packet would allow them to actually have the seamless experience. Right? So we are talking about caching, right? Caching the 3D model at the switch, and when the user change the context, then the switch can react to that change in a more efficient manner, right? Compared to CDN, where you have a full-fledged server, right? This is just a switch that can work to support this 3D streaming. All right. And this is the last project that I want to talk about. This is the project of our recent summer intern. Is the reliable teledriving in the presence of poor network condition. Right? So the teledriving is a way for you to have the teledriver, right, sitting at some office or at home and be able to control the car in that running in a remote area, right? Usually, this scenario is not possible, right? So usually you have to have the controller, right, that is in the same city as the car, right? So that the latency is smaller and you can control the car more efficiently. But this project, we want to, have be a little bit more ambitious by having like a longer latency network, and how we can enable this teledriving from the driver that is in the East Coast and the car is in the West Coast. So the control loop is like this, right? You have the sensor data that's sent to the base station, go to the internet, to the rendering server, and then the remote controller is like, okay, I'm controlling this car. When it's controlling, it's actually sending control commands back to the car, right? The car has some actuator that it can turn left, right, or accelerate or decelerate, something like that, right? So if the route trip time, of this control loop is greater than 100 milliseconds, it can cause the control command to arrive too late and potentially lead to car accident, right? So So we propose a solution where, instead of using the sensor data directly, we have to do some motion prediction and route time estimation, right? Have to predict what the car, the nearby car will be in the future, so that we have the scene that consistent with the future state of the vehicle network, right? So we can, when we send the control command, it can arrive at the right time, and then the car can be controlled safely. And we need to have some, this is kind of like it has some limitation, right? Motion prediction is not perfect when we have the situation where we expect some, a safety issue. We can, fall back to some local autonomy, like use autonomous driving when remote driving is not safe anymore, right? So we need to have that as a backup. And our contribution is we perform the robustness analysis of this motion prediction, and we study its limitation, what we can expect, what is the time horizon of the prediction, what is the latency that we can expect to have when we do this motion prediction on the GPU server, and when we expect to have some contention, right? How we can schedule the GPU tasks so that the overall compute is within the latency bound that we have, and then we inventing the confidence aware rendering for the remote driver, so that it have a sense of where to go, right? To be safe in the so that the car is safe in the remote area. All right, and this is all I have. I hope it's a good time, and thank you so much. Okay, so any questions? Okay. No question.
Thank you so much for giving the talk. So I have two questions related with the first work and the last work. So in the first work, you mentioned like you select the camera and then render the camera to the point cloud, and then you do the point cloud, right? But I'm not very familiar with the VR. But I'm thinking about this. Like there is a dump sample and then some window point cloud. So if the VR rendering just care about like the object reconstruct, or it care about where the user localization relative to the room, because I'm also doing like the control processing. Because when I do the localization, actually we cannot use so many points out. But when I want to reconstruct the object, then lots of points I have to like fusion them or merge them.
Oh,
So I'm just wondering like how do you handle like is that a fixed size from somebody, or it's just a like
you need some kind of lower bound, right?
Yeah.
Like this is, I understand that if you don't care too much about like photorealistic effect of that 3D model. For example, localization. You only know the guy here at this location. I don't need to see the 3D model, right? But if you have the use case or the application that the user care about the appearance of the 3D models, then you need to have some lower bound, right? That okay. In this project, we said it's 5,000. It also depends on the user device, right? How much it can render, how many points, right? Some device has a limitation, like okay, I cannot render more than 100K points. And that is the from upper bound that you have to also consider, right? And also, I think the object distance also has impact, right? The object is further away from the field, then you may not need that many points. So I think both, right? Both the object that you care about, and also the user location related to that object. And then for reconstruction, I would suggest you look at like, your point cloud, you can do mesh reconstruction. Or even more advanced, you have like NERF or 3D Gaussian. Get the point cloud and reconstruction. But that requires a lot more compute, not infrastructure. That requires a lot more. But for me, I see the visual quality is up a lot with those.
And then for the block work, you mentioned like you gonna send the results, like the recognition of S1 results to the server and then send the command back to the server. But have you benchmark the end-to-end latency, like because even the vehicle do the processing, and sometimes there are some AI attack, which means I attack your vehicles. So cause your model's interface time is much more longer than the processing time. And then when you send the command or the results back to the server, and then the command back to the vehicle, or the vehicle is already it's not enough for maybe hardware power. So if there are kinds of scheduling to like highlight the most important command, because for example, the recognition results can send in 30 hertz or more hertz, but sometimes maybe this range is not important, because if I do this work, then I will miss the other stuff. Like if there is any scheduling in this network.
Yeah, that's a very good question. So I think right now we still have no idea how to schedule it efficiently, but we use the same convention that if you know Waymo, right? Waymo is the autonomous driving, like they have data set, and we use the same convention that we gonna sampling the data every 100 milliseconds, just 10 FPS. Yeah, that we do the same thing, and we process the data within that time, right? We have like 100 milliseconds. Because we want to reduce the data size for the network, we run some machine learning, but like one, right? Like object detection, so that we know there are 5 cars around me and roughly at this location. But the model that we use is kind of like well studied, and it got the doable latency that we can integrate in our software. Yeah. So any other question?
Yeah, when you go back to the slides, you have this autonomy and fallback.
Oh, okay. Yeah.
Will there be a trigger if you estimate the RTT is longer than the threshold that you will start local autonomy?
Yeah, it depends on what is the threshold.
Right.
So if the scenario is not complicated, and we know from our motion prediction model that okay, now we can predict 3-second in the future, right? And if the network condition is not worse than that, then okay, that's fine. But if we know that okay, now the environment is kind of complicated, it's like in New York City, and we cannot predict more than half a second. Then right, that's also, yeah, it depends on what threshold. But it's not like because we calculate this motion prediction, we're not talking about like 500 milliseconds or 200 milliseconds real time. We're not using the raw data and do the control.